one answer here this morning that talks about the oxyazolindone. There might be one in the moment. Now the example I gave, I think, where we had this constituent here. I intentionally gave that particular example and that particular product. If you look at that, it might look a bit odd that the selectivity might be in the wrong direction to you because you benzylate this. But if we go through, we treat this with lithium dipropyl amide, that will deprotonate next to the carbon dioxide. And it will give you a particular geometry around that double bond. So there's control there already. Where the methyl group here is cis to the oxygen. And that's because this is an amide, so the methyl group down here is interacting with these two atoms on the nitrogen. Not so much all of the others, but these two have to be held in the same plane. And that is offer a severe 1,3 alliance state. So it's the first in the E, the Z configuration. This is the oxygen. Now the other important part of this is that this is a lithium salt that participates in chelation. Where I saw an emission was that there was no chelation, it was in fact drawn as that. In the example I showed, I've given you in the notes, this is actually not the preferred conformation around that bond. That would prefer to be like that, without chelation. Now what does that do for this? Well, that puts the methyl group behind the methyl group behind. And that would then direct the top face of that double bond. But in this orientation, with chelation, then you're locked into that. It's a nice tight arrangement, and that will give you selectivity from below.
I got 2 pages of answer on that.
Yeah, a full page answer.
2 pages.
2 page answer. Yeah. Twice the marks, is that true? Okay, so after reaction here, then it doesn't matter what chelation or doesn't matter where. But
yeah, so that goes on to the lead-to effect of this.
Yeah. Now, this is a case though where this is the bigger group, more substantial group. So when you see it in a paper or a product, you might actually see it represented in that orientation. So the benzyl group here in the plane of the board, if you do that, then the methyl group swings forward. Okay. Methyl group is in front. These substituents, but only after you've gone through that product. And then there's a conformational change. These are equivalent. The only difference between this and this is free rotation around that single bond. So you haven't changed configuration. Selectivity.
But does that have to do anything with the actual rate that the forming is run? The size of that ring?
The size of
that ring? Yes.
This is a 5mm ring. It's virtually planar situation. So there is advantage in having that. There are similar auxiliaries that are 6mm. And there you've got to be careful. You've got to have your substituents so that they lock the conformation in a particular planar arrangement. And they get the steric hindering groups swinging around in other directions. Chelation is important
I think you had it up a second ago, but it's gone again. Could you just go through quickly what would happen if there was no chelation? Like, for example, I think you had the HMCH co-sol. Was that destroyed, or remove any chelation with the lithium and then you get a different product?
It would destroy the selectivity. So you would probably get an equal mixture of reaction on both places. It certainly prefers the other conformation, but there's a lot more freedom of rotation. So although it's preferred, there is some degree of rotation around this, so you get some conformation like this just because of that rotation in a lot of the other ones. So you probably get preferential reaction from the top plate. So the selectivity actually might be from the top plate, but the selectivity wouldn't be very good. The beauty of this is that it holds quite rigidly, very stable conformation, and that leads to the product. Where lots of chelation has, where I've given you examples of that, is where you do an alcohol type reaction with it. So you use this as a glutamate and then reacting with an aldehyde. And this becomes originally a chelate, but you lose the chelation, there is that rotation, and the preferred conformation so that these groups lie outside or inside the six-membered ring of the transition plate. But all of that's in your notes. I think the details in the report. That's again probably a case that's going to be like the last case we gave. Really the high end of understanding all of this. You've got to understand all the Crown models, the simple enough stereoselectivity and everything that goes around that, and then putting that together. What I'm pleased that you're feeling more comfortable with that, because really that shows a lot of understanding that you are feeling reasonably confident with the simpler models that I've talked about, and now you can actually see that you can actually deal with much more complex cases simply by putting some of these tools to put in place now, using the Crown selectivity and aldehyde strain, simple dose stereoselectivity tests, put that together and actually come up with some proper deductions of quite complex models. And you will forget them. Not after 3 hours, but after a week or time, or maybe a year. But when you go back to it, then you'll quickly refresh your memory.
You can use these on IDs as well, I guess. Like
the chair is very important with lots of things around understanding stereochemical outcomes. A lot of, I don't know, we teach very much at CPAs, but direction of eliminations and things like that is controlled by this first conformation and rates of reaction. So elimination of HCl, for example, from neighbouring positions